In part number 2 here, the first one we're asked to use this graph to find a couple of velocities, and the first one says to find Albert's average velocity. So this graph is Albert's right here, and I'm going to zoom in a bit. Now from 2 to 6 seconds, so I'll leave my calculation over there. There we go. So from 2 seconds to 6 seconds, and this is Albert's curve right here, so that dot and that dot right here, this is the slope of this secant line is what we're finding here. And so at this point here, notice it's just a little bit below 30. You see that's 20, that's 40. So I estimated the distance at 28 there. And I estimated that this looks to me like it's just below 10. So that's why I used 9. So the difference between the two distances right here and here would be 28 minus 9. And it goes from 2 seconds to 6 seconds. So 6 minus 2 is 4 seconds. So Albert would have traveled a distance of about 19 meters in 4 seconds, and 19 divided by 4 is 4.75. So that's the average between 2 and 6 seconds. Now in B here it says determine average instantaneous velocity at 4 seconds. So at 4 seconds would be right here. So I'm drawing a tangent line there, and that's this blue line here. And so I'm actually going all the way from here right down to this point right here. And so the distance right there would be pretty close to 70, and the distance right here would be 0. So that's why I did 70 minus 0 in the numerator. And this is a time of 16 seconds, and that's pretty close to 1. So that's why I have 16 minus 1 in the denominator. And so basically 70 divided by 15 is 4.7 meters per second, would be the instantaneous velocity of 4 seconds. So let's go back to the same size here. And in question number 2, we're asked to use differences to determine the degree of the polynomial. And so in the first one here, and you have to make sure that you evaluate or subtract the y coordinates in the correct order here. I'm going to bring my graphing calculator over here. So you actually go -1, because it's a change from 27 down to -1. So to get that difference, you would type in -1 and subtract the 28 from it. And so that's a difference. Oh, I subtracted the wrong thing, sorry. 27. And so that's a difference of down 28. So from 27 to -1 is down -28. From -1 to -7 is down -6, because if we type in -7 and subtract -1, same as -7 plus 1, which is -6. From -7 to -3 goes up 4, actually. From -3 to -1 goes up 2, and from -1 to -13 goes down 12. So the first set of differences are all different, so it's not linear. So -6 take away -28 is 22. 4 take away -6, same as 4 plus 6 is 10. And we get differences of -2 and -14 here. So again, the second differences are not the same, so it's not quadratic or second degree. But if we go 10 minus 22, it's -12. -2 minus 10 is -12. And -14 minus -2 is -12. So the third sets of differences are all the same, so that's why it's a third degree or cubic polynomial function. For the next one, 0 minus 43 is -43. -7 minus 0 is -7. And we find that the first differences are not the same. Let's do second differences. -7 minus -43 is positive 36, because it's gone up 36 from -43 to -47. 5 take away -7 is 12. 17 minus 5 is 12. Now, it almost looks like I might have made a mistake here, that, maybe the 36 isn't right, because these are both the same. Maybe it's quadratic, but 53 minus 17 is 36, so these second differences are not all the same. Now, 12 take away 36 is -24, 12 minus 12 is 0, and 36 minus 12 is 24. So these are not all the same, but 0 take away -24 is 24, and 24 minus 0 is also 24. These sets of differences are all the same, so it's a fourth degree polynomial function, or a quartic function. And number 3 here asks to solve completely by factoring. And to do this, I use synthetic division to do the factoring. So I'm writing 2, -5, -1, and 6. And remember, you only really need to try factors of 6. You actually try factors of 6 over 2, but do the whole numbers first. -1 actually is a factor of 6 that works here. So -1. And remember, you can actually, if you have a graphing calculator, you can actually find those numbers fairly quickly by graphing the function. And let's see here. Let's just do the standard -10 to 10 axis. And so you see, this is why -1 works. If I trace, go to -1, the y-coordinate is exactly 0. So it looks to me as well like 2 might work here too, and that's why 2 actually also works. So we could go trace to 2 as well. See, the y-coordinate there is 0. So that's a way you can find the numbers fairly quickly. So bring the 2 down here. -1 times 2 is -2. -5 and -2 add to -7. -7 times the -1 is +7, and add that to the -1, you get 6. 6 times -1 is -6. Those add to give a remainder of 0. So the -1 worked. It gives us a factor of x plus 1. The 2 also looks like it works, so I'm going to do 2 here next. So bring this 2 down. 2 times 2 is 4. Add the 4 to the -7, you get -3. -3 times 2 is -6, and once again 6 and -6 add to 0, so the remainder is 0. So x plus 1 is a factor, x minus 2 would be a factor, and 2x minus 3 is the other factor. So that's what this cubic factors into. Those are the 3 linear factors. So if we set x plus 1 to 0, we get -1. If we set x minus 2 to 0 equal to 0, we get 2. And if we solve 2x minus 3, and maybe I'll do that one here, 2x minus 3 equals 0. Bring the 3 over, so we would have 2x equals 3, and divide out the 2, so we get 3/2. So that's the 3 solutions for A. Remember, when doing these, you're not asked just to factor, you're asked to solve. Some people stop at this factoring and forget that they're actually solving an equation to write out what x or whatever the variable is equal to. So for B here, this 16x should come over to the left. And so this is what we're actually factoring. And notice that there's a common factor of x in all this. So I'll factor an x out before we even get into any synthetic division. And so again, we could go back to the graphing calculator and graph. So now you could actually graph this, but because the x is factored out, we can actually just change it to 3x cubed plus 8x squared minus 4x. Let's insert a 4 here, and then minus 16. And so you see, it looks like -2 is a double root. And we could trace -2, and it is. So that's a reason why we could do the -2 twice here. So I write down 3, 8, -4, -16 for my synthetic division, and I'll do -2 here. So bring the 3 down. -2 times 3 is -6. Added to the 8 is +2. Times -2 is -4, and -4 and -4 add to -8. -8 times -2 is +16, and that add to the -16 gives a remainder 0. So x plus 2 certainly is a factor. -2 looks like it should go in a second time, so I'll do the -2 again into the 3x squared plus 2x minus 8 factor. And so bring the 3 down. Times -2 is -6. Add that to the 2, we get -4. -4 times -2 is +8, and adding that to the -8 gives a remainder 0. So this would, don't forget the common factor of x here. This is actually x plus 2 twice, so x plus 2 squared, and then 3x minus 4 is the other factors. It's quartic, so you should expect to have 4 factors. If we set x to 0, we get 0. If we set x plus 2 to 0, we get -2. And similar idea here when we set the 2x minus 3 equal to 0. If you set 3x minus 4 equal to 0 and solve for x, you get 4/3. It's this, the opposite of the -4 here, over 3, so it's 4/3. For question number 4, it says solve without using technology. And so we would want to factor this x squared plus 4x minus 32. Look for two numbers that add to 4 and multiply negative 32, which would be positive 8 and negative 4. So it'll factor into x plus 8 and x minus 4. And so the zeros to this quadratic would be at negative 8 and 4. So that breaks down in the number line into numbers below negative 8, and then between negative 8 and, that should be a positive 4 there. I actually have x is greater than 4. I don't know why I have a negative there. Should be a positive there. So below negative 8, between negative 8 and positive 4, and then above 4. So in each of these factors, we would check a value. So below negative 8, for example, negative 10. If you put negative 10 in here in place of x, negative 10 plus 8 is a negative value. If you think of a number between negative 8 and positive 4, for example, 0. 0 plus 8 is positive, so that's positive. And above 4, like 5 or 6, 6 plus 8 would be 14, so that's positive as well. For negative 4, x minus 4, sorry, a number below negative 8, for example, the negative 10 again. Negative 10 minus 4 is negative, so we have a negative here. Between negative 8 and positive 4, a number like 0, 0 minus 4 is still, so that one's still negative. And then above 4, like for example 6, 6 minus 4 is positive 2, so that factor is turned to be positive. So this is the product that we're looking for. The product of a negative and a negative is a positive. The product of a positive and negative is a negative. And down here for the last one, the product of a positive and a positive is positive. Now, we're looking for where it's less than 0, so we're looking for this negative 8. And so the solution is x is between negative 8 and, again, that should be positive 4. I'm not sure why I had a negative there. We'll change that to a positive. So that's the solution. Values of x between negative 8 and positive 4 are what makes that less than 0. For b here, we would have to factor the 2x squared minus 11x minus 6. So look for two numbers that add to negative 11 and multiply to negative 12. 2 times negative 6 is negative 12. And those numbers would be negative 2 and 1. I'm going to use the method of decomposition to factor this. So we break the negative 11x down to negative 12x plus x. And so I can factor a common factor of 2x out of here. So we factor 2x out of this and get 2x times x minus 6. And then there's only a common factor of 1 here, so we just put brackets around the x minus 6. So the x minus 6 is in common, so we factor that out. And 2x plus 1 would be the other factor. And so if we set each of these to 0, x would equal 6, and then negative a half from that one. So that breaks this number line down into numbers below negative a half, and then between negative a half and the 6, and then above 6. So that's the three intervals. So let's check numbers below negative a half, like negative 1. If we put negative 1 in here, negative 1 minus 6 is negative. And if we put negative 1 in here, negative 1 times 2 is negative 2, plus 1 is still negative, so that's negative as well. The product of actually I'll get into the product afterwards. Let's check a number between negative 1/2 and 6 in both factors. For example, 0. 0 here, 0 minus 6 would be negative, but 0 times 2 plus 1 would be a positive. That one actually changes to be positive. And then numbers above 6, like 10 for example. 10 minus 6 is positive. 2 times 10 plus 1 is also positive, so those are both positives. So the product of a negative and a negative is a positive. Between a negative and a positive would be negative, and positive gives you a positive. So looking for where this is greater than or equal to 0, so we're looking for the two positives. And so the solutions would be x is less than or equal to negative a half. Notice there's an equal to sign here, so we need to have an equality is here as well. And if this positive comes from that interval, so the other solution would be x is greater than or equal to 6 as well. For question number 5, we're asked to sketch this 5 over 2x minus 8 function. And so I'll start with the vertical asymptotes. If we set 2x minus 8 equal to 0 and solve, we get x equals 4. So x equals 4 is a vertical asymptote. It's where the function is undefined. And so we'll investigate how the function behaves to the immediate left and right of that. So to the immediate left of 4, I took 3.99 and put 3.99 in place of x. And actually maybe I'll do that calculation here. So this is what it looks like. The numerator there is 5 and divided by 2 times the 3.99 minus 8. And so that's where we get the negative 250 from. And so that implies, to the immediate left of the vertical asymptote, since the y value gets so big that as you approach 4 from the negative side, the y is tending toward negative infinity. So the graph is going down like this. Well, what happens to the immediate right of that? So I took a number slightly bigger than 4, like 4.01, and did the same kind of calculation. And actually, that's pretty easy to show here. So I want to put 4.01 here. And it works out to be positive 250. And so that implies that as x tends towards 4 from the positive side, from the right, the y value is tending towards positive infinity, so it's going up like this. Well, what's the horizontal asymptote? Because the numerator is just a constant and there's a power of x in the denominator, whenever the power of x is larger in the denominator, then the horizontal asymptote is going to be y, or f of x, equals 0. And because 5 divided by a larger and larger value for x gets closer and closer to 0. You see, the larger the denominator, the closer this is going to approach 0. So y equals 0 is the horizontal asymptote. So again, take a large number for a large positive and a large negative. So I put 100 in place of x. And I guess I could show these as well. So I'm going to put 100 in here. And so notice that that works out to be a positive value. So that's why the function is approaching, as you go to the far right, is staying above 0. And to do the negative, all we'd have to do is substitute a negative in here. And so notice that it's getting close to 0, but it's negative. And so that's this one here. So as you approach to the far left, y is approaching 0 from below. Now intercepts, so it actually looks like it's doing this. Well, where exactly does it cross the y-axis? If you put 0 in place of x, 5 over 2 times 0 minus 8, which basically 5 divided by negative 8 is negative 0.625. So that's the y-intercept right there. And there are no x-intercepts because the horizontal asymptote is y equals 0. So we join those together. It's going up here, and then to the far right, it's staying above the x-axis, approaches down like this, crosses at negative 0.625, and stays below the x-axis to the far left. For number 6, you're asked to find the asymptotes for each of these following functions. So for the vertical asymptote, we would set 4x minus 12 to 0, bring the 12 over, it becomes positive, divide out the 4, and you get 3. So x equals 3 is the vertical asymptote. The horizontal, because the powers of x are the same, it's x the first in top and x the first in the denominator as well. And so the horizontal asymptote will be found by taking the ratio of the two dominant terms. The highest power of x in the top is the 6x and the 4x in the bottom. And so 6/4 reduces to 3/2 and the x's divide out. So y equals 3/2 or 1.5 would be the horizontal asymptote. For b here, you need to factor the x squared minus x minus 2. So I factored it into x minus 2 and x plus 1 because negative 2 and 1 add to negative 1 and multiply negative 2. And so if we set x minus 2 to 0, equal to 0, we get x equals 2, and we set x plus 1 equals 0, we get negative 1. So there's two vertical asymptotes, x equals 2 and x equals negative 1. The horizontal asymptote is y equals 0, like the previous example, because the higher power of x is in the denominator. Up here, it was actually just a constant on top and a power of x of 1 in the denominator. But even if you have x in the numerator and an x squared in the denominator, the higher power is still in the denominator. So y equals 0 would still be the horizontal asymptote. For number 7, you're asked to solve each of these. And so the first thing you should do is find a common denominator for the 1/3, or the 3, the 5m, and the m, which would be 15m. And so I multiply everything by 15m. So 3 goes into 15 5 times, so it's 5m times 1, which is 5m. 5m goes into 15m 3 times, so basically it's negative 3 times 7, so that's negative 21. And m divides out with this m here, and so 4 times 15 is 60. And so that's what that becomes after you multiply by 15m both sides. So add 21 to both sides, or bring the 21 over and add to the 60 to make 81, and we divide out the 5. So 81/5, or about 16.2, actually it's exactly 16.2, is the answer for 7a here. For 7b, we have denominators of x plus 4, x minus 2, and then x minus 2 times x plus 4. So the common denominator would be x plus 4 times x minus 2. So we multiply everything, both sides, by x plus 4 times x minus 2. And on the left here, the x plus 4s divide out, so we're left with x times x minus 2, which is x squared minus 2x. This x minus 2 will divide into that one, so basically we've got negative 3 times the x plus 4, so negative 3 times x is negative 3x, and negative 3 times the 4 is negative 12. And then plus, and for question number 8 here, we're asked to use a numerical method, which means you need your calculator, to approximate the instantaneous rate of change for this function at 2.8. So what you do is you take, and this is really a slope calculation, this is really y2 minus y1 over x2 minus x1. And so we take a number close to 2.8, so I use 2.79. So my x values are 2.8 and 2.79. And so in your calculator, we would have to type in 2 times, and I'll do the 2.8 one first, plus 7, bracket, divided by, and in brackets, x minus 3, so 2.8 minus 3. Close bracket. So that's this calculation here. That's where the negative 63 comes from. And of course, to do the 2.79 is fairly easy here. We just bring that up, and go 2, and then insert a 9. And similar on the end here. And oh, I've got 2.29 here. I don't know why I did that. 79. Oh. 7979. There we go. So that's where this number comes from. Now, it's subtract negative 59.9, so that's the same as plus 59.9. So if we take negative 63 and add 59.9, and you want to keep a few decimal places, so don't round too quickly here, over, and the difference between the x values is 0.01. So that's where the negative 310 comes from. So that's the instantaneous rate of change at 2.8, or a very good approximation for it. For question number 9 here, the radius of the Earth is 380 kilometers, and space shuttle is 300 kilometers above the Earth. So the radius of the orbit here would be this radius of the Earth plus the 300, so that's why we add those. So the radius is 6,680 kilometers. And so the space shuttle travels around the Earth almost a full revolution, but not quite, through an angle of 11 pi over 6 radians. See, 12 pi over 6 would be 2. And so you're asked, how far does the shuttle move along this partial orbit? So we use arc length is radius times the angle of rotation. So we're multiplying the 6680 by 11 pi over 6. So that's the exact value. If you multiply this 36,740 by pi and divide it by 3, you get 38,474 kilometers. So that's how far the space shuttle would travel through that part of the orbit. For question number 10, it says use a compound angle identity. Rewrite this as one single trig ratio and then find its exact value. And so we look for the trig ratio that has like sine, sine, cos, cos, and that's the cosine one. The cosine, well, a minus b actually. And so notice cos A minus B would be cos A cos B and then plus sine A sine B. So notice the sine is first. So because they're added, you could write the sine A sine B and then plus the cos A cos B second. You could rearrange this and that would be fine. And so to write as one trig ratio, it's the cos A minus B1 because there's a plus in the middle here. And so we would have to subtract pi over 3 and 3 pi over 4. So get a common denominator. Multiply this by 4 top and bottom, you get 4 pi over 12. And this one by 3, you get 9 pi over 12. And so that subtracts to negative 5 pi over 12. So this would be the same as the cosine of negative 5 pi over 12. Well, what does that equal to? Well, let's find the sines and cosines. That's why the unit circle is here for all these two angles. So pi over 3 is here. The sine is root 3 over 2. And for 3 pi over 4, the sine is root 2 over 2, so multiplying root 3 over 2 by root 2 over 2. The cosine of pi over 3 would be the half, and for 3 pi over 4, the cosine is the negative root 2 over 2. And so this would be root 6 over 4, and then minus root 2 over 4, and so we have a common denominator, so we could write this as the cosine of negative 5 pi over 12. That's the one trig ratio, and its exact value would be root 6 minus root 2 over the 4. So flipping on to the question number 11 next, determine the average rate of change for the function between 0.2 and 1.1. So 0.2 x value would be about here, and 1.1 would be about here. So we're drawing a secant line between those. So, and you're reading and again, this is the slope calculation. So the y-coordinate there is a little more than halfway from 6 to 7. So I estimated at 6.3. The y-coordinate there is about 3. And then the x-coordinates are 1.1 and 0.2 you're subtracting. And so that would be 3.7, and this would be 0.9 divided 3.7.9 to get a little over 4. So about 4.11 is the average rate of change from this point to this point. For number 12, you're asked to solve these on this interval, and actually let's go get that unit circle, because we're going to need that down here for these questions. So the first thing we have to do is factor this. So we need to find two numbers to add to negative 7 and multiply to negative 8, because 2 times negative 4 is negative 8. And so that would be negative 8 and positive 1. So I'm going to use decomposition to factor this. So we decompose or break down that negative 7 sine theta into negative 8 sine theta plus 1 sine theta. There's actually a 1 here, but we don't have to write it. So you can common factor out of this a 2 sine theta, and be left with sine theta minus 4. And there's no common factor, or the common factor is 1, so you just put brackets around the sine theta minus 4. And factor it out here, and the other factor would be 2 sine theta plus 1. Well, if we set this to 0 and bring the 4 over, we get sine theta equals 4. The sine or cosine cannot it has to be between negative 1 and 1, so it can't be above 1. So for 4, there's no solution. So for the negative a half 1, well, actually that comes from setting this to 0. So bring the 1 over and divide it to 2, so that's where the negative a half comes from. And so where is sine negative a half? Well, sine is positive in these two quadrants, it's negative in these two quadrants. So at 7 pi over 6, the sine is negative a half, so that's one solution. Sine is also negative a half here, which is that angle, or 11 pi over 6. And let's bring this down here a little more for the next one. For number 2, you have 2 cos squared plus 3 cos theta minus 2 equals 0. And so again, decomposition to factor, we need to find two numbers to add to 3 and multiply to negative 4, which is 4 and negative 1. So we break that 3 cos theta down to 4 cos theta minus 1 cos theta. And we can common factor a 2 cos theta out here. So we get cos theta plus 2 when we factor the 2 cos theta out. And the only factor here is a negative 1. So we factor a negative 1 out, and we have negative, in brackets, cos theta plus 2. And so cos theta plus 2 factors out, and then we get 2 cos theta minus 1. If we set this equal to 0, we get negative 2. And again, cosine or sine can't be below negative 1. So for negative 2, there's no solution. For this one, when we bring the 1 over and divide it to 2, we get a half. Cosine is positive in these two quadrants, the first and the fourth, so we should be looking there for, if you remember, cast for solutions. Well, where is cosine a half? Cosine is a half right here at an angle of pi over 3, and if we reflect the x-axis down here as well at 5 pi over 3. So those are the two solutions for that trig equation. In question number 13, we're asked to prove, 3 identities. And the first one, we're asked to prove that sine theta equals tan theta cos theta. The right side is the tan theta cos theta, and I always try to start with the larger, more complicated side, so I would consider the tan theta cos theta to be the larger side here. And so I'm going to use the trig ratio that tan is sine over cosine. So I'm going to change the tan theta into sine theta over cos theta. And then we're multiplying that by this cos theta. So this cos theta in the denominator divides out with this cos theta in the numerator. And so we're just left then with sine theta, which is what the left side is equal to. So that's the first one proven. For the next one, I would consider the left side to be the more complicated looking side. So I'm going to write the sine, left side is the sine theta plus cos theta cotan theta. And so I'm going to start with my sine theta here, and I'm going to replace the cotan with cos over sine. And now, so once I do that, I'm noticing I'm going to have a denominator of sine here, but this has a denominator of 1. So that's why I'm going to multiply it by sine theta over sine theta top and bottom. And then instead of having another step to do this, I'll end up with a common denominator here to begin with. So we have sine squared plus cos squared in the top over sine theta, and that's equal to 1. So we're trying to show that this is equal to secant theta over tan theta. Well, it's okay in identities to work with both sides independently. So my right side is secant theta over tan theta, so I'm going to change my secant into 1 over cosine, and the tan theta into sine over cosine. And so I divide, that's what this line here right here means, by multiplying by the reciprocal. So we start with the 1 over cos theta and multiply by the reciprocal here of sine over cos, which is cos over sine. The cosines divide out, and I get 1 over sine theta. And so I've shown that both sides are equal to 1 over sine theta. So the left and right sides are the same, so the identity is true. And last identity here in the review, we're supposed to show that 2 cosecant 2x times tan x is equal to secant squared x. Well, cosecant is the reciprocal of sine. So cosecant 2x would be the same as 1 over sine 2x. So I can rewrite this as the cosecant 2x as sine 2x in the denominator. There's the reciprocal. So I'm going to change the tan x into sine x over cos x, and sine 2x into 2 sine x cos x. That's one of the identities for sine 2x. And so these 2's divide out, and so I have this sine x over cos x. I'm going to multiply it by the reciprocal of sine x cos x, which would be 1 over sine x cos x. So the sines divide out, and we're left with 1 over cos squared, which is equal to secant squared x. And so that's what the right side is, so my identity is proven. For question number 14, we're told that the sunset time varies sinusoidally with time. The sunset time for the town of Parry Sound can be modeled by this equation. Sunset time is 1.75 cos, and it's 2 pi over 365 times d minus 172 days, plus 18.4. So you're asked for how long a period of time, in days, is the sun setting earlier than 7 p.m.? And so this is what the function looks like. So my line across here would be the 7 p.m., which is 1900 hours. So this is actually just y equals 19 here. And so if you trace in the calculator, so here's my graphing calculator with the two of those. So notice that looks an awful lot like that graph there. And so just to show you the functions, there's the function typed in and the 19 line. And so using technology, if you have access to a graphing calculator, and I just went in the wrong menu, so second, calculate, I want to find intersections for these two graphs. So I can go to number 5 here. And you need to point a little bit to the left of where that point is. So I'll go to there and hit enter. And for the second curve as well, it doesn't matter what your guess is. And so that's how you can use the calculator to find that it's at about 101 days. And then so we want to find the next one as well. So I want to go close to this other point over here. Okay, so I'm getting pretty close to that point now. So second, calculate, and intersection, and second curve, guess doesn't matter. Okay, so it's telling me the other one's about, well, pretty close to 243 days. So from about 101 to 243 days. So that's the, and of course, so 243 minus 101. So for about 142 days, the sun sets above there. So for any day below 101, the 101st day of the year, which is about April 10th, or after the 241st day a year, which is August 31st, the sun is setting after 7 o'clock in the evening. For number 15, you're asked to evaluate the log of 93 base 6. So we would take the, and this is what it looks like. So the log of 93 and divide it by the log of 6. And you get that number. And so we could check that. So that means that if we raise 6 to this power, we should get 93. So I could actually type in 6 to the power of my last answer, and I'll get exactly 93. If I type in 6 to the power of and use a few decimal places, it'll be close, but not exact. 5297, yes. Pretty close to 93. So that's how you can check that that is correct. For question number 16, 4 to the x equals 50. So in order, since the x is in the exponent of this power, we use the logarithm. So you actually can take the log of both sides or just rewrite it in the equivalent log form. They end up being the same thing. So I took the log of both sides here and used the power law to bring the x down. So it's x log 4 equals the log of 50, and then I divide out the log of 4. And so they divide out on the left side here, and we get the log of 50 over the log of 4. And so the log of 50 divided by the log of 4 gives us about 2.82 is the answer. So 4 raised to the power of 2.82 is pretty close to 50. If we use more decimal places, we'll be even closer. For this next one here, just put the calculator over here. For number 9, again, the exponent is in the x is in the exponent. So we take the log of both sides and bring the 5x down. So 5x log 9 equals the log of 221. And then divide out the log of 9. And so they divide out. So we get 5x equals the log of 221. And now I want to solve for x. So I divide out the 5. So it's going to be this log 221 over log 9 and then divided by 5. Now, this is actually the same as the log of 221 base 9, so you can use the change of base formula to write that as that. But in order to evaluate it, I would still need to do, using my calculator, the log of 221 divided by the log of 9. And so that's the top part, and then I'm going to divide that by 5. So that's where my 0.4914 to 4 decimal places would come from. And again, we can check to see if that's correct. 9 to the power of 5 times 0.4914 should work out to be pretty close to 221, and it is. And of course, if I use my last answer, I would get exactly 221. So number 17, it says evaluate each of these without the use of a calculator. So notice these are both log base 9s, so, and we're adding the 2, so we could rewrite it as one log by multiplying the 3 and the 27. So it's a log base 9 of 3 times 27, which is 81. Now 81 is 9 squared, so I can rewrite that 81 as 9 squared. And if those bases are the same, then this is equal to the exponent, so that would just equal 2. You can also say here, well, what this is equal to is 9 raised to what power gives you 81, which of course is 2. For B here, let's use the power law to bring that 3 up and write it as 25 to the power of 3. I'll also write the 25 as 5 squared, and the reason I would do that is because then I have this and the base is the same power, as the same number. And so my 5 squared becomes cubed when I bring the 3 up. So power over power, you multiply the exponent, so this would be 5 to the power of 6. And very similar to this one, those 9 and the base of 9 were the same. So these two bases are the same, so that would equal 6. And number 18 says simplify each of the following using the 3 laws of logarithms. And so the log of 144 base 3 minus the log of 6 base 3, we're subtracting, so this would be the log base 3 of 144 divided by 6, which is 24. And so that's how we can simplify it into one single logarithm. For b, the 4 would come up and become a power of the 2x. Now remember, the whole 2x, not just the x. Really common error here is to write this. Log base 7 of 2x to the 4th. But you see, the whole 2x is raised to the power of 4. You need brackets around there. So when you evaluate then the 2x to the 4th, you get 16x to the 4th. And I didn't do anything to the second logarithm here. We really need to do this first. So again, don't forget the 2 to the 4th is 16. And so we're subtracting two logarithms, and they're both base 7, so we can combine to one logarithms. It would be this 16x to the 4th divided by the 8x cubed. And so that's why we do this. And then we can simplify this. 8 divided by 16 is 2. X to the 4th divided by x would be x cubed in the numerator, and the y cubed is still in the denominator. So that's how you write that as one single logarithm. Similar for c here, I'm going to use the power again. The 1/3 comes up as a power of the z. Now power of a third means the cube root, same thing. And so the 5 comes up, so log x to the 5th. And the 2 comes up here as well. So when you have u cubed to the power of 2, you multiply the exponents, power of power law, and so you get u to the 6th. So right as one single logarithm then, we have the log, and notice that both are all base 10. There's no base here. So it would be z cubed x to the 5th. These are added, so we multiply those two and subtract this one, so the u to the 6th goes in the denominator. So that's how you write as one single logarithm. For question number 19, we want to solve this logarithmic equation. So I'd like to have the logarithms both on the same sides. That's why I brought this logarithm to the left. And so the minus turns into a plus here. And same idea as the rules up here. We want to write this as one single logarithm. So I'll multiply the x minus 5 by x plus 3. So x times x is x squared. X times the 3 would be a 3x, and then this would be a negative 5x to give you negative 2x when you add those together. And negative 3 times 5 is negative 15. So we have this equals 1. Now, how you can change this so it's no longer an equation with a log is this would equal 9 to the power of 1, or 9 to the power of 1 equals this x squared minus 2x minus 15. So I want to solve this, and this is just a quadratic equation now, so I'll bring the 9 over. Negative 15 minus 9 is negative 24, and I want to factor this. So what adds to negative 2 and multiplies negative 24? And that would be negative 6 and 4. So x minus 6 and x minus 4 are the factors. If we set each of these to 0, we get 6 from this one and negative 4 from this one. Now, 6 is okay. When I put 6 in here, 6 minus 5 is positive, 6 plus 3 is positive. Okay, that's okay. But when you put negative 4 in here, negative 4 minus 5 is negative, and you cannot take the log of a negative value. Same here, negative 4 plus 3 would be negative 1. So negative 4 is not a solution. So 6 is the only solution here. For b here, what we should do, or what I did, was I combined these two logarithms together. So they're added, so we would just multiply the 10 by the x minus 2 to get 10x minus 20. And we have one single logarithm on the right side here. So if you can write both sides as just a single logarithm, in this one it was a little bit different, the last one, because we had the 1 on this side as well. So if we write them both as log base 4 both sides, then we can drop the logs. The logs don't divide out. Like you shouldn't be doing this. We're not actually dividing out the logs. Okay, so don't do that. That's not the correct thing to do at all. So we just drop the logarithms, because if these are equal and the log bases are the same, then this 10x minus 20 would equal the x squared plus 5x minus 14. Now I kind of switched sides, both sides, but that's okay. Just so my signs work out better on the left, that's all. So I'll bring the 10x over, subtract 10x from 5x, you get negative 5x, add 20 to both sides, and negative 14 plus 20 is 6. And we'll factor this. So what adds to negative 5 multiplies to 6, which would be negative 3 and negative 2. So we'll factor into x minus 3 and x minus 2. If we set each of these to 0, we'll get 3 for this one and 2 for this one. Now, 3 is okay, but x can't equal 2, because if x was 2 here, you'd be taking the log of 0, which you cannot do. You can't take the log of 0 or a negative. And so that's why 2 is not a solution. The only solution here would be the 3. For C, in this one, we have 9 to the 3x plus 1 equals 27 to the x. And because we can write the 9 and the 27 both as powers of the same base, that's a good strategy to use to solve this. So 9 is 3 squared, and 27 is 3 cubed. So there's my 3 squared, and this would be 27 to the 3x. It's actually 3 to the third to the power of x, but you multiply the exponents, that's why it's a 3x. So I multiply this 2 by the 3x plus 1, so that's 6x plus 2 in the exponent there. And very similar to this last one, like at this point I have both sides as log of base 4, so this would equal this. Well, same idea here, but with the powers instead. I have power of the same base, so the only way these two things can be equal, since they're both base 3, is if this exponent is equal to this exponent. So I can set 6x plus 2 equal to the 3x. You do not divide out the bases, okay? You just drop the bases because the exponents must be equal here. And so I brought the 2 over to the right, so that's why it's negative 2, and the subtracting 3x from 6x is 3x on the left, and I divide out the 3, so x would be negative 2/3. For D, and I believe this is the last of the exponential ones, yes, I want to factor this. This is very similar to factoring if we had x squared minus 4x minus 5. The same idea as that. What adds negative 4 multiplies negative 5. And so the way we would factor this is because this is a 5 to the 2x, then these both don't start with x's like that one would, but they would start with 5 to the power of x's, because 5 to the power of x times 5 to the power of x, if we were to expand this out, would give you 5 to the 2x. Remember, when the bases are the same, you add the exponent, so x and x adds to 2x. Well, what adds to negative 4 and multiplies negative 5 is, again, negative 5 and positive 1. And so this would factor into 5x minus 5 and 5x plus 1. If you expanded the rest of this out, if you multiply these together, let me get my pen back going here, that would give you negative 5 times the 5 to the x. And if you multiply this together, it give you plus 1 times 5 to the x. And if you add that negative 5 and 1, you get negative 4, so that's where that term comes from. And of course, negative 5 times positive 1 is this negative 5. Oh, let's get rid of our scribbling here. So, and that one too, probably. So if we set 5x minus 5 equal to 0 and solve for x, we'll bring the 5 over, so we get 5x equals 5. So x would have to equal 1 because it's 5 to the power of 1 that it gives you 5. If we set this one to 0, bring the 1 over, we get negative 1. But 5 to the power of x cannot equal negative 1. You can't raise a positive base to any power and get a negative, so there's no solution there. So the 1 here is the only answer for D. For question number 20 here, the magnitude m of an earthquake is measured using the Richter scale, which is defined as m equals the log of the intensity of that earthquake divided by some standard low-level earthquake. So I naught is the standard that everything's measured against. You're asked, what is the Richter scale reading for an earthquake that is 45,000 times more powerful than the standard low-level one? So it was 45,000 times more powerful, then this ratio they're telling you is 45,000. So it's going to basically just be the log of 45,000, which works out to 4.7. So the Richter scale reading would be 4.7. For B, how much more powerful is a 6.8 Richter scale earthquake than a 4.0 scale one? So using the formula, this would actually be the difference between the two, not just the reading of 1 like we did in A here. So M2 minus M1, if I call M2 the larger one and 4 this M1 the smaller one, so that we really need the difference between the two of those, which is 2.8, would equal the log of this ratio. How much more powerful? We're really asked what's that ratio of intensities. And so the base here is 10. So 10 to the power of 2.8 would equal this ratio. And so 10 to the power of 2.8 is 631. So that means that earthquake is 631 times more intense than the 4.01. For question number 21, we're told that a 60 milligram sample of a radioactive isotope decays to 50 milligrams in 4.7 days. So we're asked to determine the half-life, and then I have another question B here. So the half-life is the amount of time for half of it to dissipate. And so this is the general formula. The amount after a certain time is the initial amount times the half to the power of the time over the half-life. H is what we're trying to solve for here. And so we're told that the initial 60 goes in place of A naught, goes down to 50, so I put 50 in place of A of t in 4.7 days. So the t here is 4.7. And we're trying to solve for h. So the first thing I would do is divide out this 60. So these divide out, and so 50 divided by 60 is 0.833, or 0.83 repeating, would equal the half, or 0.5 to the power of 4.7 over h. Now again, I'm trying to solve for h. H is in the exponent, so that's why I need a logarithm here. So to convert this into its equivalent log form, the exponent would equal the logarithm of this base 0.5. And so we would evaluate this by using our scientific calculator. And so we would take actually let's do the logarithm first. The log of 0.8333 divide by the log of 0.5. So that's that logarithm, and now we have to divide 4.7 by that answer. So that's where the 17.9, it rounds to days, comes from. So the half-life would be about 17.9 days. So now we have the formula, same formula as I used right here, except we now know that h is 17.9. So we're asked how long will it take for the amount of the isotope to decrease to 20 milligrams. So 20 goes in place of A of t, and we're solving for time. And so I divided the 60 again. 20 divided by 60 is 0.3 repeating. And so we would just have a half to the power of t over 17.9. So very similar over here, this exponent t over 17.9 would equal the logarithm of 0.3 repeating divided by, to the base of 0.5. So the way we evaluate that is the log of this divided by the log of 0.5. So I'll multiply both sides by 17.9 here to isolate the t. So when I do that, t would be 17.9 times this logarithm. And so we would have 17.9 times the log of 0.3 repeating divided by the log of 0.5, and that's where my 28.4 days comes from. So it takes about 28.4 days for the 60 milligram sample to decay to 20 milligrams. For 22 here, we're given these two functions, and we're asked to graph h of x, which is the f of x function minus the g of x function. So this minus the 3x, so basically it's x squared minus 2x plus 1 minus 3x. So what I did here is I found a table of values for the f of x function, for the 4x squared minus 2x plus 1 function. So I'm substituting negative 2 and negative 1, 0, 1, 2, 3, etc. in place of x, and these are the y values I get. And I did the g of x function as well. So excuse me. So I'm substituting the same negative 2 to 2. Well, actually, I ran out of room for the 3 here. I put 327 there. And in place of x. So, for example, 3 to the power of negative 2 is 1 over 3 squared, or 1 over 9. When I put 0 in here, 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9, etc. And so these are the two functions for f of x and g of x. So h of x is the difference between them. So we would take the f of x function values and subtract the g of x function values from them. So 19 minus 1/9 is 18 and 8/9. 5 minus a third is 4 and 2/3. Negative 1 minus 1 is negative 2. 1 minus 3 is negative 2. 11 minus the 9 is 2. And 29 minus 27 is 2 as well. And so this would be my h of x function. So I could plot this. And if you plot these, -2, and it's off the top of my graph, almost 19, and then -1, 4 2/3, 0, -2, etc., you will get this h of x function, which looks like that. So just plotting those points. Now we're asked to solve the inequality that basically f of x is less than g of x. So where is f of x less than g of x? So I did graph the f of x function and the g of x function. So this is the g of x function and this one's the f of x function. The blue one's the f of x function. And so you can see that they cross here and about here. So that point, I'm just reading it from the graph here, that point's close to -0.5. It's about -0.43. And about 1.55, around there. Now there is another place where the two functions cross, but you can't see it from these two graphs. Remember what we graphed here was the difference between the two functions. So if I actually were to solve, let me write this on the page here. If I were actually solving, I'm going to take the 3x over here to the 3 to the power of x to the left. 4x squared minus 2x minus 1 minus the 3 to the x, whoops, is less than 0. So basically that's what was graphed in the first part here. So if we find where that's less than 0, well, that's the solutions. So where these two cross is the same place right there where this function, this h of x function, hits 0. And that intersection point right there, see, that's the x coordinate here. But then also you see this 3 to the x function actually starts increasing faster than the parabola, and so there actually is a place up here where they cross. And we would find that actually it's too far up in the graph here, but we would find that right here. So it's between 3 and 4. I think I used my graphing calculator to find it's close to 3.2. This is, I mean, I'm graphing this by hand, so it's not perfect. But that number actually is about 3.19. So between -0.4 and about 1.55, and then also greater than 3.19, the function, this inequality is the solution for it. For C here, asked to find and simplify g of f of x and f of g of x. So g of f of x means you're putting f of x into g of x. So you're putting this in place of x. So it's 3 to the power of that quadratic. So that's the first part in C. F of g of x means you're putting the g of x here in place of x here and here. So it'd be 4 times this 3 to the x squared minus 2 times the 3 of x plus 1. And so that's what that looks like. Now, we can simplify this. Remember, power of power, you multiply the exponents. So that'd be 3 to the power of x times 2 is 2x. Remember, that's not 12 to the 2x. The 4 is not raised to that power at all. So it's just 4 times 3 to the 2x minus 2 to the 2 times 3 to the x plus 1. So that's f of g of x. Now, the last question asks, why would you expect g of f of x and f of g of x to be different? And they are. This function is certainly not the same as this one. And that's because the composition of functions, combining functions in different orders or different ways, is not commutative. The commutative property in like adding integers, for example, says that 5 plus 3, for example, should equal 3 plus 5. We add them in different orders, we get the same thing. Both of those give you 8. But combining functions in different orders, like substituting f into g, is not the same as g into f. And so that's why we would not expect that to be the same most of the time. And that's the end of the review.